Okay, so hi everyone. So welcome back to the other session of BEEE. So we'll get back to the actual things and let's wait for uh, 2 or 3 minutes so that everyone would join. So meanwhile, just anybody can help me in knowing the things, that is whether the screen is visible and my voice is audible or not. Okay, so just anybody can reply, right? So that I can proceed. Yes, sir. Yes, sir. Okay. So yesterday, if you guys having any doubt, meanwhile you can ask me, right? So in the last 2 minutes, while I was explaining Lenz's law, right, the power has suddenly gone, right? So that's a problem. So I will discuss it. And if you have any doubts regarding yesterday's class, you could definitely ask me. Yeah, please send the recorded video. Yeah, okay, I will definitely send it. So, right. So this is the same class, right? Same class will be recorded. Okay, no problem. So the same video, same entire class will be recorded somewhere, right? So now I think I can see that. Yeah, yes, yes, it's available actually. Okay, you can see it. You will get it definitely. I will definitely post it. And if you guys have any doubt, you please ask me in the chat box, right? Okay. So today's participant strength is 44 only, right? So 45. Okay, 8, 11. Okay, okay, okay. Right. Okay, right. So without wasting time, so I will go to the PPT. Right. Right. Just a quick recap I will give you. Right. So induction motor. So we are discussing about the induction motor, right? So I said the fifth unit is consists of both induction motor and synchronous machine, right? So here at this instant itself, I said induction motor is also known as asynchronous machine, right? So why it is asynchronous machine? That I will discuss today. Okay. So why the induction motor is also known as asynchronous machine. You can see here I am straight away asynchronous. Right. Okay. Asynchronous machine. So the induction motor is also known as asynchronous machine. So right, this is it. So why it is asynchronous machine? We'll definitely discuss today. Right. So now get back to induction machine. Right. So we discussed the induction machine is having a rugged construction and very cheap, little maintenance, all those things, and it has stator and rotor. Right. Stator will have three-phase winding. Right. So and there are two types of rotors. One is squirrel cage rotor, another one is wound type rotor or slip ring rotor. Right. So you better find the differences. You go to Google search, you identify the differences between squirrel cage rotor and slip ring rotor. So there would be many differences and you can easily identify those things, right? So that's it. Here the diagram you can see, right? So that is here the second diagram, so which has a rotor winding and slip rings and external resistances. So that means the slip ring rotor is having the flexibility of connecting external resistances into its winding. But squirrel cage rotor, the rotor terminals are not available outside. Okay, once again I am repeating, the main difference between squirrel cage rotor and slip ring rotor is that, okay, in squirrel cage rotor, the rotor terminals are not available outside, right? So you don't have the flexibility of connecting anything, whatever you want to the rotor winding. You don't have that flexibility. But the slip ring rotor, so that is this particular diagram, the second diagram, right, in which you can see the out of the dotted box, the three terminals are comes and they've been connected to external resistance. Not only resistance, if you want, you can connect it to anywhere else. So that is the feasibility of slip ring induction motor, right? So this is it. This we have discussed, right? So the construction point, and in the afternoon session, so right, so we discussed RMF, rotating magnetic field. How does a rotating magnetic field is produced, right? Hope you understood this particular concept, though it is completely equation sort of thing, but I made it, I thought I made it somewhat simpler. I don't know whether I have succeeded or not. Okay, so but so the main thing is this rotating magnetic field. So let's, right. So this rotating magnetic field, right. So that means there are three fluxes, so phi r, phi y, phi b. So these are the three equations, right. So out of these three fluxes, there will be one resultant flux of phi r, which has a magnitude of 1.5 times 1.5 times this phi m, 1.5 times this phi m, right? So that is it. And at what speed this resultant magnetic field rotates? That is at synchronous speed. It is at synchronous speed, that is ns, right? That also we seen. And if you want to change, right, so here we followed ryb, that is why it is rotating in clockwise direction. If you want to change the direction of this rotation, you have to change the phase sequence, that is instead of ryb you have to go for rby. Okay, so that is it, right? This all things we have seen, and ns is equal to 120 f by p, right? What is f, right? Can anybody tell me in the chat box, right? So now the other participants also joined, and can anybody recall what is f, right? What is f? So on the screen, bottom of the screen, right, you have some formula, ns is not the stator speed, it is a synchronous speed, right? So what is f over here, right? What is f? Okay, so you tell me what is f. So that is frequency only, right? In electrical, f means frequency. Which frequency? Which frequency? That is what I want. Yeah, someone said it's a supply frequency. Okay, supply frequency, but you are giving supply to stator winding or rotor winding. That is important. Okay, yeah, stator frequency. Only one answer. Only one answer. That is 4H4, a good one, right? Supply frequency of stator, yes, yes. Okay, right. So now guys, okay, that's enough. Okay, all of you just be patient and listen to my question patiently. You just listen to my question, right? So here, at this point of the supply to the motor, I told one thing, that is DC machine is dash excited, induction machine is dash excited. So you just type it in the chat box. Induction machine is dash excited, whether it is singly excited or doubly excited. Induction machine is, my question is whether it is singly excited or doubly excited induction machine. Yes, right. So I'm expecting many answers, right? So induction machine is doubly excited or singly excited, and it would be better if you write the answer also. If you just type the answer in a short or brief form, Okay, fastest finger first, right? Okay, yeah, yeah. Someone said DC is doubly excited, induction motor is singly excited. I am expecting at least one answer. Why induction motor is singly excited? Let's see whose finger is fastest. Okay, okay. That is from A section, that is 418. Yes, okay. That's sufficient. So that's all for today's question session, right? So, okay. So guys, see, the purpose of asking questions is to just to have some conversation, right? So because I should know whether you are getting the class or not, right? So right. So I will tell you why the induction machine is singly excited, because we give three-phase AC supply to stator only, right? Only stator winding is connected to supply, only stator is excited. So that is why the induction machine is singly excited. But coming to DC machine have two windings. One is stator winding, rotor winding. Stator is having field winding, rotor is having armature winding, right? So both are connected to DC supplies, right? In the DC machine, both the windings, that is field winding and armature winding, both are connected to uh, DC supply. Both are connected to supply. That is why they are, that DC motor is doubly excited one, whereas induction motor is singly excited. And in the DC motor, you have the terminology called uh, armature winding, field winding. But induction motor, we don't have such a terminology, right? Right. So we have stator winding, rotor winding. That you just remember. Okay. So right. Yes. Okay. Okay. So right. So now let's get back to quickly to the point which we need to discuss. Right. So okay, guys. Once again, see the working of three-phase induction motor. Somehow we understood, right? So we understood in the last class the working of a three-phase induction motor. So guys, see the what is principle of induction motor? That is induction principle, right? Principle means point of uh, on what point this motor operates. That is what principle, right? So that is on the based on the induction principle. What is induction principle? The power will be transferred from stator winding to rotor winding, right, through induction principle, just like a transformer, right? If you have not completed transformer, it's okay. You have seen the flux is the medium between stator winding and rotor winding. There is no physical contact, there is no electrical contact, right? So that's it, right? So now coming to working, how the motor starts rotating, right? So that is it. You see, right? So I'll you just see point by point, right? So it would be somewhat helpful, right? Though it takes some time. When a three-phase winding, 1 minute, right? When a three-phase winding is energized from a three-phase supply, a rotating magnetic field is produced. This is obvious. The entire afternoon session, yesterday's afternoon session, we concentrated on rotating magnetic field only, right? So how it produces? We have three-phase winding on stator. Obviously, on the rotor also we have three-phase winding, right? But we give three-phase supply to the stator winding, then a rotating magnetic field is produced. This is fine. First point is okay, done. First point is completed. And what about the second point? This rotating magnetic field. What is the speed of this rotating magnetic field? That is ns. What is this ns? Ns is synchronous speed. What is the formula for synchronous speed? That is 120 f by p. And you excuse me for my writing, because for the mouse it's not that convenient. Okay, so right, this is speed of the rotating magnetic field. What is the magnitude of that rotating magnetic field? That is 1.5 pi m, right? That's it. And this is the field. This is the rotating magnetic field, generally r, capital R M F, rotating magnetic field, remember. So right, this rotating magnetic field passes through air gap and cuts the stationary rotor conductors. So you see, this is stationary rotor conductor. So far, the motor is not rotating. We just connected three-phase supply. Then field is produced that is rotating, and that is cutting the rotor conductors. Now, what will happen? Faraday's laws of electromagnetic induction. What will happen? EMF, first EMF will be induced. First EMF will be induced, and then current flows. And then current flows. So here, this point EMF induced is skipped away, right? So now thereafter the mechanical force, that means the motor starts rotating, right? So here, yesterday someone has asked me, right? So the field is, let's say the field is rotating in clockwise direction. That is, what is the speed of the field? That is just now in the second point, ns, synchronous speed, right? I said the rotor rotates at a speed of nr, nr, right? So the question is, why the rotor rotates only in the same direction as the stator field, right? You see the directions over here. You see the directions, right? So here the ns, stator field, is rotating in clockwise, and similarly rotor rotates in the clockwise but with some lesser speed. Suppose it is rotating at 1500 rpm, it will rotate at 1400 rpm, right? But in the same direction. Why same direction? That is what this Lenz's law, right? So here, why the motor is rotating? Because of current. So from where this current has come? Because of the cutting action. So that is field is cutting the stationary rotor conductors, right? So what is Lenz's law? This is effect opposes the cause producing it. What is the effect? Current produced. What is the cause? That is flux cutting action, or the relative speed. So the produced current or the motor rotation will try to reduce the current magnitude. So that is why it rotates in the same direction. Okay, so that is the case, right? So now we will get back to another thing. Next slide. Right. So this we seen in the last class, right? So that is ns and this is nr, right? So this we seen, right? So now see, okay. So right. So what is slip? So right. Slip means here, uh, just now I said the rotor rotates at slightly lesser than the stator flux, speed of the stator flux. That is why, right? So that is what the slip. The rotor is slipping away from the stator field. So that is why it is slip speed, right? What is percentage slip, right? So that is ns minus nr by ns, right? What is the difference of the speed? That is ns minus nr, and with respect to ns, that is what the slip, right? So now you see, you remember the value of slip at standstill, right? So try to see, this is slip speed. Yeah. So I think uh I will go, I will try to concentrate more on this point, right? So guys, see, what is slip speed? What is slip speed? You can see the spotlight on the screen. What is slip speed? Slip speed is the difference, right? A difference of both the speeds, both the speeds, in the sense that is stator field speed and rotor speed. That is what slip speed, right? So when the rotor is stationary, what is the speed of the rotor? That is zero, right? If nr is equal to 0, if you substitute here, what is the value of slip? That is 1 or 100%. That's it. That's it. You remember this, right? Now see, my question at the starting of the class, right? I written something. Induction motor is asynchronous machine. Induction motor is asynchronous machine. Why it is asynchronous? Because why it is asynchronous? Because the rotor speed cannot be equal to synchronous speed. I'm once again repeating, guys. Please listen. The rotor speed, that is nr. NR cannot be equal to NS. Why? Why it cannot be equal? Suppose the rotor conductors are rotating at NS. That is same as uh, stator field speed. This is rotor conductors, right? So and you do have, suppose this is the speed of flux. This is the speed of flux. What is the speed of flux? Ns, right? And these are rotor conductors. Let's say this particular conductor, right? Or else this particular conductor. Okay, so you see this particular conductor, conductor 1, right? So now see this, if, and what is the speed of this rotor conductors? That is NR. Guys listen, right? What is this NS? Speed of flux, right? This is the instant, at one particular instant, where it is here, and this is conductor 1. So if both are equal, if NR and NS, if both are equal, what will happen? They both, this conductor 1 and flux, both rotate at same instant, both cross this y1 at same instant, this axis at same instant, this axis at same instant, this axis at same instant. That means there is no, the conductor 1 is facing same amount of flux at every instant. Okay, guys, are you getting? If NR is equal to NS, what will happen? This conductor will always face the same amount of flux. There won't be any change in flux. But what is Faraday's second law? That is E is equal to, right, N into minus N. We forgot about that. N minus N into d phi by dt, right? So now, if NR is equal to NS, the conductor 1 will always face same amount of flux. So this d phi by dt will be equal to 0. So what will be equal? EMF induced in the rotor conductor 0. If EMF is 0, what will be the current in the rotor conductor? 0. If there is no current, the motor principle won't be satisfied. So that is the reason always the NR, that is rotor speed, will be equal to, will be not equal to, will be always less than NS, right? So that is why it is known as asynchronous machine. If NR is equal to NS, NR is equal to NS, and still the motor is rotating, that means that is known as synchronous machine, because it is rotating at synchronous speed. The rotor conductors are rotating at synchronous speed. That is why it is synchronous machine. But in the case of induction motor, so let's say induction motor, NR will always be less than NS only. NR will be less than NS only. If the induction motor cannot be able to rotate at synchronous speed, either it will rotate at less than synchronous speed, or it will not rotate at all. Okay, you remember the induction motor, either it will rotate at less than synchronous speed, otherwise it will not rotate. Okay, so that is the case. That is the reason induction motor is also known as asynchronous machine, because it always rotates at other than synchronous speed. Okay, and in some cases, the rotor speed will be greater than ns also. That is known as induction generator. That is beyond your syllabus. You forgot about it. Okay, right. So this is about uh, the induction motor, why it is known as asynchronous machine. So I know it's a somewhat conceptual thing. It's a bit difficult to understand also, right? So at the end of the session, we do have some sort of conclusion. I will conclude with some questions, right? I will give the answers also. Don't worry, right? So this is what slip. Okay, slip means relative velocity. Suppose if I am running at 20 kilometers per hour. Okay, so I am at the age of 32 or 30, right? I could not run it faster than you. So I am running at only 20 kilometers per hour. And you are younger, so that is 24 or 22 age. Okay, you are in the first year, maybe 21. Okay, 10 years younger than me. Okay, so you can definitely rotate it, run at 40 kilometers or 30 kilometers per hour. So what is the uh, relative speed between both of us? That is at 10 kilometers, right? If I am, so that is what relative speed. So similarly, the stator field is rotating at ns. Okay, so let me use the spotlight. Stator field is rotating at ns, but what is the speed of the rotor? Nr only. So what is the relative speed? That is ns minus nr, right? So that is the case. So now get back to other slide. So that is what you understood. What is slip means? Slip means just uh, a, a difference, relative difference, right? So now see rotor current frequency. Okay, so now what is happening? The EMF is induced in the rotor winding. So which EMF, whether it is AC or DC? Obviously AC, right? So now starting, okay, uh, before this, I will I will go to some slide. So let me get the clarity. Okay, so wait for 1 minute. Okay, so guys, you just tell me. Okay, so what is the time right now? Okay, we have some time. Okay, so all right. So you have a question on the board. What is the speed of this data? So you just type it in the chat box, right? So one by one. So I will see you quick answers, right? What is the speed of this data? Yes, speed of this data. You give me, right? So give me the answers. Speed of the stator, ns. Ns is equal to 120 by p. Ns. Mm, zero speed. Yes. Okay, okay. That's sufficient. Right, that's sufficient. So that is speed of the stator is 0 RPM. Guys, guys, stop typing, stop typing. Right. So listen. Okay, so it is 0 RPM. Why? Because the I said stator speed. Stator is a stationary one, right? Stator does not rotate. Stator is a stationary one. So that's why 0 RPM. Okay, next question. What is the question? So that is speed of the stator field. Speed of the stator field. Stator field. What is the speed of the stator field? So this I need not to ask. Uh, what is it? That is obviously uh, ns rpm. That is ns. What is the formula for ns? That is 120 f by p. Next, third question. Okay, guys, see the question. Okay, you only type the answer for third question. Okay, speed of the rotor yet standstill. Rotor yet standstill. Read the question properly. Okay, third question, speed of the rotor at standstill. What is it? What is it? I could not see answers. Okay, what happened? Yeah, someone said I think zero. Okay, okay, so that means you have doubt. If you are saying I think zero, so that means you have some doubt. Oh, someone is saying one. What does it means one? Is it 1 RPM? Guys, see the question. Speed of the rotor yet stand still. Rotor yet stand still. Stand still. Okay. So that means cycle is at standstill. What is the speed? 0 RPM. 0 RPM. Right. So that is 0 RPM. So that's it. That's it. That's it. So that is uh, speed of the rotor at standstill is 0 RPM. Next, fourth question. What is the speed of the rotor? Rotor speed. Yeah, we rotor speed. Rotor speed, you know it. So that is NR, right? So now see the question by question. Okay, so let me use the spotlight. Okay, so you should not get the doubts. Speed of the stator, right? So because stator is a stationary one, that's why 0 rpm. Speed of the stator field rotates, right? It rotates at synchronous speed. Yeah, I am running out of time. We have only 10 minutes. Okay, so and maybe I will restart the session also, right? So you could join it, right? Okay, now speed of the rotor at stand still, stand and still, both are giving the same meaning, right? 0 rpm. Speed of the rotor during running, that is nr rpm. Okay, now next question, speed of the rotor field. So this I haven't discussed. So this is also ns rpm. Okay. So where this rotor field comes, right? You may get a doubt, sir. We are giving three-phase supply to stator winding, then a stator field comes and it rotates at ns and it cuts the rotor conductors at standstill and then rotor starts rotating. But meanwhile, what is happening between 3 and 4? When the stator field is cutting the rotor conductors, what happens? EMF is induced. What happens next? Current is produced in rotor conductors. Then that rotor current produces a rotor field, right? That rotor field also rotates at synchronous speed. Okay, so remember, rotor at standstill is 0 rpm, rotor speed is nr, rotor field speed is ns. So this is it. This is it. Next question, right? So all of you see the question, relative speed. I just given the example with my running speed and with your running speed. So we got some relative speed, right? So right. So now, yeah. Now answer to sixth question. I am expecting an answer for sixth question. Right? That is relative speed between stator field and rotor. So you have answers for from the above answers. You could give the answer from the above discussion. You could give the answer, right? What is the speed of stator? Okay, okay. I am seeing some answers. Someone is saying slip. Okay, someone is saying slip. Okay, okay. Yeah, yeah, yeah. Okay, I'm seeing a good response. Okay, so at least 15 members, 15 to 20 members are responding. Okay, so right, that's very, very nice. Okay, so now guys see relative speed between stator field and rotor. What is the stator field speed? That is ns. What is the rotor speed? Nr. So that means what is the relative speed between these two? Subtract both. That is ns minus nr. Not nr minus ns, because we concluded that from the previous discussion nr will always be less than ns. So that's why ns minus nr is the answer. Ns minus nr is the answer. Now, now guys, I have another question. Of course it is not on the screen, but you listen to my question carefully. What is the relative speed between what is the relative speed between stator and stator field? Relative speed between stator and stator field. Relative speed between stator and stator field. What is the relative speed between stator and stator field? Yes, yes, it is ns. It is ns. Okay, good. Okay, good, good. Not minus ns. It's just a relative speed. Okay, so yes, ns. Right. Now, what is the relative speed between? Other question. Other question. What is the relative speed between stator field and rotor field? Relative speed between stator field and rotor field. Both are fields. Both are fields. Yes, yes, 0 rpm. Exactly 0 rpm. Very good, very good. Okay, next question. Next question. Next question. Good, 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 good. Next question. What is the relative speed between rotor field and rotor? Rotor field and rotor. What is the relative speed between rotor field and rotor? That is ns minus nr. Ns minus nr. Good, good, good. Okay, someone is asking a question, sir. Why the rotor field is rotates at ns? Okay. It leads to a lengthy discussion. Okay, so I definitely I suggest you to go to read a book. Okay, so please read a book. Okay, so someone asked me that question, right? So now I will close this question session, right? I will get back to another thing. Okay, not series RL circuit. Okay, right. So now see, okay, so guys, listen carefully. So the heading of this slide, I will try to complete this slide. That's it for today. Okay, within 4 minutes, hope we could complete it. Right. So this heading is rotor current frequency, or you read it as rotor frequency. That's sufficient. Okay. So what is happening? The stator field is rotating at a ns speed. Okay, so what is happening? Maybe we could see here what is happening. So at starting, what is there? The stator field is rotating at ns. What is the speed of the rotor at standstill? Zero. So what is the relative speed? That is ns minus nr. Ns minus nr is zero. So the relative speed is very high. Okay, so if ns is 1000 rpm, and what is the rotor speed? Zero. So 1000 rpm is the relative speed. That means emf induced in the rotor conductors is very very high. Relative speed is very very high. Okay, that's it. And after some time, what will happen? The rotor starts rotating. Rotor starts rotating, right? So then what is the relative speed? ns minus nr. Ns minus nr. So that is the point. You see, at starting the relative speed between the stator field and rotor is ns. At starting, relative speed between stator field and rotor is ns. During running, conditions, what is the relative speed? Ns minus nr. So that is the point, right? So now if you quickly get back here, so just this is ns is equal to 120 f by p. I have rearranged the equation, and where n is the relative speed. N is the relative speed. So during running conditions, what is the rotor frequency? Fr is equal to what is the relative speed? Ns minus nr. Ns minus nr. Pi into p by 120. So this, let's see, divided multi this side ns into ns by ns multiply with. So and here you can rearrange the equation like this. Okay, let me use the spotlight. Okay, so this, you rearrange the equation, you bring this ns over here, ns over here. Now see, what is this? ns into p by 120. That is what? Stator supply frequency. Ns is equal to 120 f by p, right? So that is f, right? Ns minus nr by ns, that is what? It is s. So what's the final answer? Fr is equal to, right? So rotor frequency Fr is equal to, so that is slip times stator frequency. So now you see, what is the value of slip at standstill? At standstill, value of slip. Slip formula is this one. That is ns minus nr by ns. At standstill, what is nr? Nr is equal to 0. So then ns get cancelled. What is the value of slip? S is equal to 1. So that means what is the value of rotor frequency? Fr is equal to, that is equal to same as stator supply frequency. Whatever the frequency we are giving it to the stator, same frequency will be the rotor frequency. But later what will happen? Slip value, the nr will be nearer to it. Suppose if it is ns is 1500, nr is 1400, what is the difference? 100. What is the value of ns? 1500. So that is so you would get, yes, slip value is 1 by 15. Slip value will be less than 1. So fr will be less than that frequency, supply frequency. So, right, this is what for today's class. Okay, so let, if you guys have any doubts, you can post me in the chat box, right? So and we'll see tomorrow. Tomorrow I think we don't have class. we will see day after tomorrow, right? So if you have any questions, you just put it on a paper, right? You keep it ready for the next session, right?